So last time, Shab, we spoke about the Otto cycle, the representation of the cycle of the gasoline engine on the PV diagram, on what's called actually the Otto cycle, and we have derived last time. We have derived this relation for the thermal efficiency of an engine working on Otto cycle, which you can represent as the case of gasoline engine. But as we said, this Otto cycle is air standard cycle. The cycle actually, we have assumed all processes are reversible. We don't have any kind of losses within the system. Combustion takes place at constant volume. However, this assumption assumes that the combustion takes place instantaneously at the same moment at no time almost when the piston is at a given location. So all of these are assumptions in the gasoline engine based on the Otto cycle air standard cycle, and based on this we have calculated the thermal efficiency of the cycle for an Otto cycle to be represented as function of the compression ratio R, and also as function of the specific heat ratio constant, which is the parameter K. So for the Otto cycle, which can be used actually as a representation for the gasoline engine, we have proved last time that the thermal efficiency of this Otto cycle is equal to 1 minus 1 over R to the power K minus 1, and the K is the specific heat ratio. And this thermal efficiency, Shabab, as we have proved last time, is equal to the net work out of this cycle divided by the heat added to the cycle. And we have represented this cycle on the PV diagram, so the pressure volume diagram, and we said if this line is representing the top dead center, and that line is representing the bottom dead center. We have started the cycle from the bottom dead center at the beginning of the compression stroke, and we assume that the compression process from 1 to 2, through which actually the piston is moving up. We have in this case negative compression work. This process is isentropic compression. Isentropic means there is a process is reversible. We don't have any kind of losses. The process can be reversed to the initial state without leaving any trace on the system or on the surrounding. That means actually this process is reversible and we don't have any kind of losses. And also the process is adiabatic. So we have isentropic compression, then process from 2 to 3. This is actually a constant volume heat addition. We assume that the combustion takes place instantaneously in the gasoline engine. Once we have the spark, then the combustion takes place homogeneously at almost no time, while the piston is at a given location, which is the top dead center. Then after the combustion, we'll have isentropic expansion process, in which we can generate a positive work in this case, and this process is also isentropic, which is reversible and adiabatic. And then for process actually from 4 to 1, this is a constant volume heat rejection process. Once we open the exhaust valve in the gasoline engine at constant volume, then in this case the exhaust gases which are at high temperature T4 will be just exhausted from the engine when the piston is at the bottom dead center at almost no time. And then the piston will be moving at constant volume from state 1 up to, let's say, state 5 to exhaust the gases, and then it will be reversed again from 5 to 1, from top dead center to the bottom dead center, and then we can have the intake stroke. But this is a process from 1 to 5. This is one extra process on the standard Otto cycle, because in a standard Otto cycle we assume we don't have intake valve or exhaust valve in this case. And also we don't have exhaust or process, or we have intake process. Just we have a fixed amount of air. We don't assume even we have a fuel inside the engine. So in this case, we don't assume actually that we have intake or exhaust valve. So this process just indicated from 1 to 5 to represent the case of the engine. However, the standard Otto cycle, we assume we don't have intake or exhaust valve in this case. And the net area, Shabab, and the work net, the net work produced by the cycle can be represented by the area contained actually by the point from 1 until the point number 4. We have proved last time that the work for a closed system, which is the assumption in case actually of all the standard Otto cycle, we assume the system is closed. We don't have intake air or exhaust gases. So in this case, the work for a closed system is equal to integration of BdV. And we have proved last time that this work on the PV diagram can be represented by the area under the curve. So the area contained by the cycle here, Shabab, represent the net work out of this engine. طيب how we can increase the efficiency شباب of a thermal cycle, thermal Otto cycle, which can represent as a case of gasoline engine. How we can improve the efficiency of a gasoline engine based on this relation? What should we do to improve the efficiency?
Increase the compression ratio.
Exactly. So one option شباب is to increase the compression ratio. So the compression ratio is equal to the volume, which is V1. So the here شباب the volume between the top dead center and the cylinder here. When the piston is at the top dead center, the volume is represented by the clearance volume. And the swept volume between the top dead center and the bottom dead center, we call it the displacement volume. And the clearance, the compression ratio is equal to the ratio between the cylinder volume divided by the clearance volume. Cylinder volume, which is the volume at point 1, which is V1, divided by V clearance, which is the volume at point number 2. To increase the compression ratio, in order to increase the efficiency, then in this case we have to reduce V2 in this case, or reduce the clearance volume. If I reduce the clearance volume here, so if the bottom dead center is existing here for the same cycle, then in this case we can add this part of work to the work in it. And that means in this case the work out will be increased by this amount, and in this case as we increase the network, so in this case the efficiency will also be increased. But is there another option شباب to increase the efficiency? So to increase the efficiency of a gasoline engine, we can increase the compression ratio. However, if we increase the compression ratio in gasoline engine up to above a given limit, so in this case we may have what? What will be the problem in this case?
Engine knocks.
Engine knocking in this case. So as we increase the compression ratio, so in this case the pressure and temperature, the maximum temperature here, which is at 0.3, will be increased in this case, and also the pressure will be increased, and there is a high possibility that we will have self-ignition inside the cylinder in this case. And that's why in case of gasoline engine, the compression ratio will almost limited between 8 up to 10.5. Okay, and that can result in a thermal efficiency of Otto cycle about 60%. But as you know, شباب, this is not the efficiency, the actual efficiency of a gasoline engine. Usually the efficiency of gasoline engine about 30, 35. This is the maximum efficiency of a gasoline engine. But here for Otto cycle, it can approach 60%, because in this cycle we assume actually all processes are reversible. We don't have any kind of losses. We assume we don't have intake or exhaust valve. So all of these are assumptions that can result actually in the limiting efficiency or the maximum efficiency of the engine. But in reality, and also شباب, in this case we assume we don't have any kind of losses, heat losses within the system. In gasoline engine we have a cooling water circuit, and we have oil for lubrication, and those two systems can consume about 1/3 of the output power of the engine. It's consumed actually in the absorbed by the cooling system. So almost the efficiency of gasoline engine about 30%. But another option or another way to improve this efficiency is we can improve the efficiency by adding more heat. So if I added more heat here to this process, instead from 2 to 3, I just extend it, let's say 3 prime. So if I increase the amount of heat added, and in this case the temperature, maximum temperature will be increased, then in this case we can do the expansion process from a higher point. And in this case we can add this value actually to the network out of the engine. So if we increase the value of Q added as being increased to the engine, that means in this case we can also improve the efficiency. So how we can increase the Q added to the engine? The amount of heat added to the engine, how we can increase it? Q added is equal to what? Is equal to M dot fuel multiplied by the heating value of the fuel. We are burning the fuel at a given mass flow rate. And this is actually the energy content of the fuel, which is the heating value. That means this is actually the amount of heat added to the engine. So to increase the amount of heat added, I have to increase what? The mass flow rate of fuel. And to increase the mass flow rate of fuel, usually gasoline engine are working at excess air factor almost equal to 1, or equivalence ratio equal to 1. So if I want to increase Q added, I have to increase the mass flow rate of fuel. That means in this case, I have to increase what? Mass flow rate of air. So that the ratio between fuel and air can be kept almost constant to keep the operating condition near the stoichiometric combustion in gasoline engine. And this is what is done in case of turbocharged engine. In case of turbocharged engine, we use a compressor in order to compress the air, more amount of air. It will increase the amount of air, and in this case, will increase the amount of fuel as well. Increasing the amount of fuel will increase the heat added to the engine. Increasing the heat added will result in better thermal efficiency in this case. That's why the turbocharged engine should have better thermal efficiency than actually the normally or naturally aspirated engine without turbocharge. Is that clear, Shabab? Is it clear?
It's clear.
So this is the efficiency. As I told you, Shabab, this efficiency for the Otto cycle is a standard cycle in which we assume we don't have any losses within the system. All processes are reversible. Reversible process, Shabab, means a process can be reversed without any effect on the system. We don't pay any kind of energy to reverse the process. That means this process has no losses, and also we assume we don't have any losses from the engine to the cooling circuit or anything. So that's why this efficiency can give us indication about the limiting efficiency of a gasoline engine that cannot be reached in reality. طيب, let's define another parameter which is called actually the indicate mean effective pressure. Indicate mean effective pressure. Actually, the indicate mean effective pressure is not a real pressure. It is just a representation. It gives us indication about the ratio between the work in it out of the engine divided by the displacement volume. This parameter, Shabab, is used. It is actually one of the specs of any car. If you go to buy a car or something, so in this case you will find one of the parameter, one of the very important specs actually is the indicate mean effective pressure, which compare actually different engine that have actually different displacement, so that it compare actually the power output of different engine of different displacement volume. So let's say we have a car of 1.6 cc. Okay, this car is given work in it or power output at a given value, one given value. We may have actually a turbocharged car of a cc, let's say 1.2 in a small car. This is the cc of the car, of a turbocharged car, but this car is turbocharged. That means we have higher mass flow rate of air, higher mass flow rate of fuel. That means we have higher heat added in this case. Okay, so for the same, this actually lower cc, so the size of the engine is much lower. This is 1.2 cc cubic centimeter, and this one is 1.6. And in this case, maybe actually the one of 1.2, which is turbocharged engine, may result actually in higher work in it out. So in this case, we compare the work out of different engine that have different displacement volume. If we have an engine with higher displacement volume, what is the displacement volume, Shabab? The displacement volume is the volume displaced by the cylinder from the top dead center to the bottom dead center, which is equal to pi over 4, which is the volume of the cylinder. Pi over 4 d squared multiplied by the stroke L, and if we have number of cylinder, we have to multiply by z, which is the number of cylinder. This is the displacement volume, or what we call actually the engine cc. Okay. So if we have an engine with higher engine cc, higher displacement volume, higher engines, bigger engine size, it should give in this case actually higher work in it. And in this case, the value of indicated mean effective pressure should be high. But if we have another engine with the same displacement volume and it can give higher work, higher indicated work, that means actually this engine will be better because it will have higher indicated mean effective pressure. And usually turbocharged engine, for the same displacement volume, if we have a turbocharged engine of the same cc, 1.6, this turbocharged engine should be given actually higher work in it out in this case. And for the same V displacement, if work in it is higher, that means the indicated mean effective pressure will be higher in this case. So indicated mean effective pressure is a parameter that compares the work out of different engines that have different displacement. So if we have a bigger engine size, it should give in this case bigger work in it out, and in this case the indicated mean effective pressure should be higher in this case. But if we look here, this is the indicated mean effective pressure, will equal to work in it divided by the displacement volume. Displacement volume is the difference between V1 and V2. So it will equal to work net divided by V1 minus V2. And this work net, this is equal to the thermal efficiency is equal to work net divided by Q added, which is equal to 1 minus 1 over R to the power K minus 1. So work net in this case will equal to Q added multiplied by the thermal efficiency divided by V1 minus V2. Let's substitute here, so it will be Q add thermal efficiency, which is 1 minus 1 over R to the power K minus 1 divided by V1 minus V2. If I put V1 as common, so it will be 1 minus V2 over V1, which is 1 over R. Okay, so if you just rearrange it, it will be indicated mean effective pressure. That should equal to Q added divided by V1 multiplied by R over R minus 1 multiplied by 1 minus 1 over R to the power K minus 1. We got a little bit complicated, ya shabab. Do you see it, ya shabab? So let me write it again. So the indicate mean effective pressure will equal to work net, which is Q added multiplied by the thermal efficiency divided by V1 minus V2, which is V1 minus V2, which is the displacement volume. So Q added multiplied by thermal efficiency will be Q added divided by, let's take V1 as common, so it will be 1 minus 1 over R, V2 over V1, 1 over R, so multiplied by the thermal efficiency 1 minus R to the power K minus 1. And this is the indicated mean effective pressure. If I divide it by pressure V1 and divide it here by pressure V1, then in this case we can plot the relation between this term, indicate mean effective pressure, relation between indicated mean effective pressure divided by the pressure V1. Pressure V1 is the intake pressure at the inlet section of the cylinder, at the intake manifold. If I plot it against actually the compression ratio, function of those parameters here, and as function actually of different value of this term, which is Q added divided by V1. If you plot this relation, you will find here, as we increase the compression ratio, we should improve actually the indicated mean effective pressure. It should be increased at a given value of this term, which is Q added divided by V1. But if I increase this Q, the value of Q added, in this case, if I increase this term, increase the value of Q added, so that means in this case also the indicated mean effective pressure will be improved. And this is the case, as I told you, the case of turbocharged engine. When I increase the value of heat added, so in this case I will extend this process from 2 to 3 to 3 prime, and then in this case I will increase the maximum temperature of the cycle followed by the expansion process. And this is actually the kind of network, the value of the work that we add actually to the network, to the cycle, and in this case the efficiency should be improved. Efficiency improved, that means also the indicated mean effective pressure will be improved in this case. Okay, is that clear, Shabab?
Yeah, it's clear.
This Shabab also, as we said, as we increase the compression ratio, the efficiency can be increased, and this is actually based on this relation, thermal efficiency 1 minus equal to 1 minus 1 over R to the power K minus 1. If I increase the compression ratio, the thermal efficiency should be increased. It is starting here from 0. If we have compression ratio equal to 1, so this term will be 1 minus 1 will be 0. Increasing the compression ratio will result in higher thermal efficiency. This is the range of operation of a gasoline engine. The compression ratio is limited between almost a value of 8 up to 10.5. This is the maximum compression ratio. The compression ratio is limited by the maximum temperature of the cycle. Maximum temperature, which is the temperature at 0.3. This is the maximum temperature of the cycle. And also the maximum pressure is at 0.3. At the end of the combustion process, we should have the limiting temperature and the pressure of this cycle. But if this temperature is limited, we cannot increase too much in the case of gasoline engine if we increase the compression ratio, because in this case we may have self-ignition. So this temperature is about T3 should be lower than the self-ignition temperature of the fuel, the gasoline fuel in this case. So T3 is limited to avoid self-ignition, and also the maximum pressure in the cycle V3 is limited due to the material strength. So in case of gasoline the material strength, usually we don't use very thick material because the pressure inside the cylinder is not too much high. So it's reasonable. So the thickness of the material used and the weight of the engine will be light in this case. But in case of diesel engine, you know the compression ratio can approach a value of more than 20, maybe 22 or something. That means in this case we have to have heavier engine in this case. To improve the strength of the material, we have to increase the thickness of the engine, the thickness of all material. And in this case, the weight of the diesel engine will be much higher in this case, in order to withstand the pressure generated due to the high compression ratio in the diesel engine. As I told you here, you can see the efficiency is almost about 60% for the gasoline engine, but this is the ideal efficiency, ideal Otto cycle. But as I told you, we cannot approach this limiting efficiency because in the standard cycle, we have assumed all the processes are reversible. We don't have friction losses. We don't have any kind of heat losses. As I told you, Shabab, in case of internal combustion engine, we have about 1/3 of the engine power is just consumed actually in the cooling system and lubrication system, which is not counted here in the standard Otto cycle. And also we assume the compression and the expansion process are reversible and adiabatic, and that should result actually in a higher efficiency in this case. Also, we assumed in this cycle that we don't have fuel in this case, but in reality we should have fuel. And also in reality, this fuel does not go for complete combustion. So usually we have some fuel in the exhaust system, and that also should actually extra lower actually the efficiency of the gasoline engine. طيب here شباب also is another parameter that we can improve, by which we can improve the thermal efficiency. You can see here the thermal efficiency is function of the compression ratio, and it is function also of the parameter key, which is the specific heat ratio. Usually in gasoline engine or internal combustion engine, the charge to the engine is fuel plus air. And if you calculate the air to fuel ratio theoretically, you will find the air to fuel ratio theoretical for gasoline fuel is almost about 15. That means the ratio between the mass flow rate of air to the mass flow rate of fuel is 15. 15 kilogram air for each 1 kilogram fuel. That means the properties of the mixture will be almost dominated by the properties of the air. So that means the specific heat ratio for this mixture of the burned gases will be almost very close to the value of the specific heat ratio of the air, which is equal to 1.4. Almost it can be a value of equal to 1.3. This is the specific heat ratio if we are using a gasoline engine burning air plus fuel. Type we said here, based on this thermal efficiency, we can improve this thermal efficiency if we are using actually a working fluid that having actually higher specific heat ratio value of K. So if we increase the value of K from 1.2 to 1.3 to 1.4, as you can see, the thermal efficiency has been improved. So if I'm using another working fluid instead of air, that means in this case we can improve the efficiency. You can look here. The thermal the specific heat ratio of the exhaust gases is equal to 1.3. Type if we use the air, it will be 1.4. But we are using air already, but we have a mixture of air plus fuel, so the specific heat ratio is equal to 1.3. But if I'm using another substance instead of air, so let's say I'm using monoatomic gases like argon or helium. So in this case, they have higher specific heat ratio equal to 1.67 in this case. So that means the thermal efficiency of the Otto cycle, if I'm using a monoatomic gas like helium or argon, that means the thermal efficiency in this case will be increased. And this is one of the development, as I told you before. The ultimate goal actually is not to use hydrocarbon fuel. The ultimate goal is to convert all of the hydrocarbon fuel to be converted to hydrogen. And then we can use this hydrogen in the combustion system. One of the development in gasoline engine is the use actually of what we call hydrogen fuel argon power cycle. And in this actually for the internal combustion engine application. In this cycle يا شباب they use hydrogen as a fuel, and they use the oxidizer as a mixture of argon plus oxygen. Argon plus oxygen is used instead of air, so hydrogen will be in this case burned with this oxidizer mixture. Argon is an inert gas. It will be burned with oxygen, and the combustion product will be just water vapor plus argon. Then we can condense this water vapor, and then we will actually get back with the argon. Then we can recirculate this argon actually to the intake manifold of the engine, and then we can repeat this cycle, and then we can burn it with hydrogen in this case. Using argon يا شباب will increase the specific heat ratio K, and it will much improve in this case the thermal efficiency of a gasoline engine. يعني this argon power plant cycle, argon power cycle was invented by Robert Dibble. I think Robert Dibble here is here يا شباب in Kaust. He's existing in Kaust, and this engine is under research. But as I told you, in future we have to convert most of the engine to work with hydrogen. Gas turbine has to be converted to work with hydrogen as well. So the ultimate goal is to convert all of the hydrocarbon fuel to be converted to hydrogen. Then we can burn hydrogen, which is actually a very clean fuel that can result actually in water vapor in the combustion product. So one of the application in gasoline engine is to use the argon power cycle, in which we use a mixture of argon plus oxygen instead of air, which have actually higher specific heat ratio in this case, and to be burned with hydrogen, and it can result in this case in higher thermal efficiency. This يا شباب يعني is an extra task if you want to read about the argon power cycle for internal combustion engine. If you want to prepare a report or something, يعني this is something extra if you want to work on. Okay, but I advise you actually to read about. Maybe actually this may be one of the future engine in the internal combustion engine. Is that clear يا شباب?
Yes.
طيب here يعني an example. This chapter يا شباب will not يعني consider homework or يعني sheet for the solution. Just we'll have يعني some practice example to solve. This is one of the example here, but يعني the cycle, Otto cycle is air standard cycle. We cannot apply for gasoline engine because we have in this case we assume the working fluid is air. We don't have intake or exhaust system, so it's almost يعني reversible cycle. So in this chapter يعني I decided not to add يعني a homework. That's enough for this one. I will just give you some practice example, but just try to read them carefully. As a practice. So in this case, in this example, we have a gasoline engine working on Otto cycle, and we have the compression ratio is 9.3, and they give you the pressure and temperature and also the volume at the beginning of the compression stroke. Volume at the beginning of the compression stroke, which is at 0.1, which is the cylinder volume V1. And we need to calculate the maximum temperature of this cycle. Sorry, the maximum temperature of the cycle is given 1727 maximum temperature, which is the temperature at 0.3. And we need to calculate the pressure and temperature at all points, starting from 1 until we reach 0.4. We need to calculate the net work out, thermal efficiency. We need to calculate the indicate mean effective pressure as well. So I will be starting from 0.1 like what we have done last time. So we have temperature, pressure, volume at 0.1. So we can apply, this is the ideal, we are following the ideal gas model. So we can apply the ideal gas equation of state PV is equal to MRT. And then we can calculate the mass. Mass at 0.1 يا شباب is the same mass for all points, because we assume in the analysis that this is a closed system. So mass is fixed. So mass will equal to V1 divided by RT1. And the process from 1 to 2 is isentropic compression. So we can use the isentropic relation that we have proved last time. T2 over T1 is V1 over V2 to the power K minus 1. V1 over V2, which is the compression ratio. So we have T1 and we have the compression ratio. P, which is the specific heat ratio for air, is equal to 1.4. Specific heat ratio for air, شباب, specific heat at constant volume, specific heat at constant pressure. All of this data you can find in table A1. Also, we can use the other relation, isentropic relation B2 over B1, is the same as V1 over V2 to the power K. For the process from 1 to 2, which is isentropic compression, we have V1 over V2 and we have B1, then we can calculate B2. Unlike this, you can go from 2 to 3. 2 to 3, this is constant volume. So we can say B1 V1 over T1 will equal to B2 V2 over T2. And we have V1 is the same as V2, or V2 is the same as V3. Then we can get B3 over B2 will equal to T3 over T2. We have B2, T2, then we can calculate T3. So this is something you can just read ya shabab. A process from 3 to 4 is also isentropic expansion. I can use the isentropic relation between temperature and the volume and also between pressure and the volume to calculate the temperature and the pressure at point 4. Then we can calculate the heat added, which is from process 2 to 3, which will equal to CV multiplied by T3 minus T2. CV we can get from table A1 for air 0.716 multiplied by the temperature difference, we can calculate the heat added. Also we can calculate the heat rejected from 4 to 1 at constant volume will equal to CV multiplied by T4 minus T1. We can calculate it. And the net work, as the system is working on a cycle, net work should equal to the net heat added, which is equal to Q added minus Q rejected, should equal to the work in it. And the thermal efficiency is equal to 1 minus Q rejected over Q added, as we said last time, and we can calculate the thermal efficiency. Mean effective pressure is the work in it divided by the displacement volume, which is V1 minus V2. We have already V1 is given, and V2 over V1 is 1 over the compression ratio. Then we can calculate the mean effective pressure. So this is an ideal way to follow what is going on inside a gasoline engine, starting actually from the beginning of the compression stroke until we have the end of the expansion, and also we have the exhaust stroke. But this is based on the standard Otto cycle, which is a reversible cycle. But it can give a theoretical indication about the engine performance. It can give us a rough analysis or a rough value or very close value to the actual value, especially for the maximum temperature and the maximum pressure inside the cycle, which is the state of point number 3. And this is very important parameter in the design of gasoline engine. We have to design the engine in order to have the temperature T3, which is the maximum temperature less than the self-ignition temperature of the fuel. Okay.